When you're just sitting there at your computer, maybe you're deep into a game, got some music bumping in the background, and you're casually messaging friends on another app, have you ever actually stopped to think about what's going on under the hood? I mean, you don't have to stress about managing the memory or worrying if your mouse clicks are actually going to register. You just want to play, right? But beneath that super clean, user-friendly interface you're looking at, your computer is pulling off this wildly complex balancing act. So in this explainer, we're going to pull back the curtain. We're looking at the invisible magic that keeps your entire digital world running so smoothly, specifically CPU scheduling and hardware interrupts.
Honestly, the sheer scale of the problem is just mind-boggling when you really think about it. How exactly does your machine handle hundreds of tasks at the exact same time without just completely freezing up or crashing on you? You might look at your screen and think, oh, my computer is just doing these 3 or 4 things I have open. But the reality? The reality is way, way more chaotic. Because at literally any given second, there is this constantly shifting pool of like 400 to 500 different processes inside your system, and every single one of them is desperately begging for processor time. Some are super high priority, some are low priority. Some are incredibly complex math, and some are really basic. And they're all jumping in and out of the processing queue at speeds we can't even really comprehend. If they all tried to grab the CPU's attention at the exact same millisecond, it would be absolute, total gridlock. So to prevent that gridlock, we need a boss, a master orchestrator, if you will. And that, of course, is your operating system. To keep the whole system from crashing due to resource contention, the OS uses resource management and some incredibly specific scheduling algorithms to basically bring order to the chaos. It's playing traffic cop. It decides exactly who gets to use the CPU, exactly when, and for exactly how long. And it dynamically shifts its strategies on the fly to optimize performance. Let's actually look at the first strategy it relies on.
Okay, so the most straightforward approach is first come, first served, or FCFS. Just picture a grocery store checkout line. It's that simple. Processes get assigned CPU time in the exact order they show up in the ready queue. The CPU takes the first process, serves it completely from start to finish, and doesn't even think about looking at the next one in line until it's done. In computer science, we call this non-pre-emptive, which is just a fancy way of saying once a process starts executing, absolutely nobody can interrupt it until it's finished. Simple? Yes. Fair? Kind of.
But here's the catch. FCFS has this one major, glaring drawback called the convoy effect. Imagine you run into the grocery store, right? You just want to buy a single bottle of water, but you get stuck in the one open checkout line behind a guy with 2 overflowing shopping carts who decides he's going to pay in pennies. It's a nightmare. You are a short process getting stuck behind a massive, long-running process. Inside a computer, that exact scenario leads to terrible CPU utilization, massive delays, and just a super frustrating laggy experience for whoever is sitting at the keyboard.
So how do we fix that traffic jam? Well, the OS can switch to an algorithm called round robin. Instead of forcing everyone to wait for one massive task to finish completely, round robin is what we call a preemptive algorithm. It gives everyone a turn. Every process gets a fixed tiny slice of time, which we call a time quantum. Think of it like taking turns in a board game. Task 1 gets a few milliseconds, then the OS hits pause, saves where task 1 was at, and moves on to task 2 for a few milliseconds, then task 3, and so on, just spinning in this continuous, cyclic loop.
If we put them head to head, FCFS is definitely simpler to implement, but man, you risk those massive convoy effect delays. Round robin, on the flip side, is incredibly responsive. It actively prevents any single process from just hogging the CPU, which is exactly what you need for modern multitasking. But, and this is a big but, the master orchestrator has to be really careful here, because if that time slice, that quantum, is too short, the CPU spends all of its time just switching between tasks, saving states, loading states, back and forth. We call that context switching overhead, and it's a huge waste of power. But if the time slice is too long, well, you just degrade right back into the FCS problem. It requires absolute perfect balance.
But wait, what if a task is incredibly important and literally cannot wait its turn in the round robin? That brings us to priority scheduling. It operates exactly like that VIP priority lane at the airport. Every single process is assigned a priority level. The CPU looks at the waiting queue and immediately hands over time to the process with the highest priority score, which lets those absolutely critical system tasks bypass the regular line completely. And if a new, highly critical process suddenly arrives, the OS will instantly drop whatever it's doing, suspend the current task, and handle the VIP.
Naturally, there's a trade-off here too. If your system is constantly getting bombarded with high-priority VIP tasks, the regular, low-priority tasks might just get completely ignored forever. In the computer science world, this is literally called starvation. A process is just perpetually denied the CPU time it needs to actually do anything. So, to prevent starvation, a cleverly designed OS will use a technique called aging. Basically, as a low-priority task sits there rotting in the waiting line, the OS slowly, incrementally bumps up its priority score over time, so it guarantees that eventually it becomes a VIP itself and gets its turn.
Now, if you want to get really fancy, these algorithms can actually be combined into an even more complex setup called the multi-level queue. Instead of having just one giant waiting line for everything, the OS sets up several separate queues, permanently assigning processes to specific lanes based on what they actually are. So, for example, your interactive user tasks, the stuff you're actively clicking on, might get thrown into a high-priority queue that uses round-robin rules, keeping your apps feeling super snappy. Meanwhile, some boring background system update gets shoved into a low-priority queue that just uses first-come, first-served. It's a hybrid approach, perfectly tailored to different needs.
Okay, so we've spent a good bit of time on how the OS manages internal software processes. But what happens when the outside world interferes, when external hardware demands attention? How on earth does the CPU know the exact millisecond you've clicked a mouse button, or typed a key, or plugged in a thumb drive? Because hardware inputs are entirely unpredictable.
I love this analogy for it. An interrupt is basically like a doorbell ringing while you're head down, busy working. This is the whole concept of interrupt handling. The CPU is in the zone, crunching numbers, doing its own thing, and suddenly a hardware device sends this sharp electronic signal, an interrupt, basically yelling, "Hey, I need your attention right now." Let's look at how that doorbell actually works in real life. When you physically move your mouse across your desk, you naturally expect the cursor on the screen to track it instantly, right? Zero lag. To actually make that happen, there's a fascinating, complex series of steps occurring behind the scenes in just a fraction of a millisecond.
Let's walk through it. First, you physically move the mouse. The tiny sensors inside the mouse immediately generate an electronic signal that encodes the exact direction and distance of your movement. Those signals get chopped up into data packets and blasted over your USB or Bluetooth connection. The interface on your motherboard catches that and generates the actual interrupt signal, firing it straight into the CPU. The CPU instantly hits pause on its current task, saves its exact state, and activates a specialized little piece of software called an interrupt service routine, or ISR. That ISR is what actually updates the coordinates and moves the cursor on your monitor. Once that's done, the CPU jumps right back to whatever it was doing before. All of that incredibly complex communication happens just so you can aim your crosshairs in a video game.
Now, there is an alternative to interrupts, and it's a method called polling. If an interrupt is like a doorbell ringing, polling is like having a kid in the back seat on a long road trip, constantly asking, "Are we there yet? Are we there yet? Do you have data for me yet?" With polling, instead of waiting for a signal, the processor itself repeatedly checks the status of every single device at regular fixed intervals, just asking if anything needs attention.
When you compare the two side by side, the differences in efficiency are pretty wild, especially when you look at power draw and processing overhead. Interrupts are absolutely vastly superior for unpredictable events. I mean, they literally save battery life on your mobile devices because the CPU can just go to sleep. It enters a low power state and just chills until an interrupt event wakes it up. Polling, on the other hand, drains your battery super fast because the CPU has to stay awake and active, wasting all these valuable processing cycles constantly checking in on devices that probably aren't even doing anything.
So bringing all of this software scheduling together, there really is no single best algorithm. The OS is smart. It dynamically shifts between first come, first served for those simple, predictable background tasks. It uses round robin to make sure everyone gets a fair turn when you're multitasking. And it relies on priority scheduling to guarantee that your critical real-time system functions never miss a beat.
And looking at the hardware side, the exact same logic applies. You have to use the right tool for the job. Interrupts are the undisputed champions for unpredictable inputs, like your mouse and keyboard, or for remote IoT sensors that run on a battery and need to sleep for 99% of the day. But if you are, say, programming an industrial manufacturing robot where events have to occur at hyper-specific, highly predictable, fixed intervals, well, in that specific case, polling actually simplifies the design and guarantees controlled latency, because you don't have the overhead of constantly switching contexts.
So here's what I want you to take away from this explainer.
The next time you've got 50 browser tabs open, a heavy game running, and music streaming, and your device miraculously doesn't burst into flames or lock up entirely, take a brief moment to appreciate the staggering level of complexity happening right out of sight. Will you thank the master orchestrator? Because honestly, this combination of clever scheduling algorithms and lightning-fast interrupt handling, that's the invisible magic making all of modern computing possible. The next time you boot up, you've really got to ask yourself, what else is your computer hiding from you?